How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business, and the physics today has uncommon enchantment and beauty. It has to do with soap bubbles and soap films and surface tension and why raindrops are round and other such enchanting matters. Let me do now, first on the blackboard, some introduction to the first experiment, which you will be enchanted by, I am sure. Let us consider a T-tube, so, with an arm here, and a little funnel or thistle tube there, and a thistle tube here, and let's say a rubber tube there, so I can blow some air in here by mouth. Now I am going to dip the ends of these funnels into some soap solution and blow some bubbles. So you see what has come to me in my 58th year, an old man, a physicist, playing with soap bubbles. But I have spent 40 years playing with soap bubbles and have not yet tired of it. So I'm going to blow two bubbles. Now I could blow two bubbles, both the same size, but there would be no interest in that because there'd be no problem. I like to pose problems. So I am going to blow a small bubble on this side and a big one on this side. S for small and B for big. And I can do that because some of the tubing here is flexible and I can shut it off and blow more air into that one than into this one. Now, having blown the two bubbles, I close off this connection with the outside atmosphere. So the bubbles are connected with each other, but not with the outside air. And the logical question that must be asked is this: what now happens? And invariably everybody says, well, they get equal, because there's more stuff in here that comes over here, and when they get equal, there's the same stuff in both, and then they stay equal. But this is not so. It turns out that the smaller bubble blows the bigger one bigger. As one student once said to me, it looks, Professor, as them that has gets, which is a very good expression of it. Why does this happen? Well, the fact remains that the pressure in the smaller bubble is greater than in the bigger bubble, which ravages reason. Now let me do this. I have here the two little funnels, and here is a soap solution, and there is soap. And I squeeze here. And now I shut off the connection with the outside air and watch the smaller bubble get smaller. Watch it. We're a little twisted there. Watch it. Look at it. Look at it. And not only does it get smaller, but the smaller it gets, the faster it gets smaller. Watch it. Watch it. Watch it. Watch it. Look at that. Look at that. I'm going to blow it again. Watch it now. And I would call your attention to the beautiful colors in the soap bubbles, which has to do with the colors. There it is. Look at it, getting smaller and smaller, smaller. And this is well, it's incredible that the smaller bubble should blow the bigger one bigger. And for those of you who are equipped with the mathematics, the pressure is inversely as the radius of the bubble. So we are dealing here with pressures in bubbles. 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 B-U-B-B-L-E-S. Now, bubbles is one kind of business, and drops are quite another. So I'm going to show you some wonderful experiments, first with surface tension on a liquid, and then on the shape of droplets. Consider the following. I have here a little paper cup which already has some water in it, and I'm going to pour more water into it. More water. More water. And I hope you see that the surface is quite rounded up, quite much higher than the cup. Look at that. Isn't that incredible? Incredible. Notice how much above the cup that surface of the liquid is. Indeed, let me go back and make a comment about that. I have sometimes had a vessel filled with water so that it overhangs like that. And this surface film has great tenacity. Indeed, have you not seen little bugs flitter about on the surface of a quiet pool of water without getting their feet wet? Now, I'm going to show you that on this high elevated surface of water, the membrane surface is so tight that I can float steel on it. And here is a needle which is steel. And I'm going to try to drop it on there and hope to show you that steel can float on water. Watch it now. I must be very careful because I may puncture the surface film and it'll sink. There it is, there it is. Oh, man, am I delighted. There is the needle floating on the water. Steel floating on water, which shows you the tremendous tenacity. Now I spoke about droplets. Here I have some mercury and a medicine dropper, and I am going to take out some mercury and form a drop. And look it. When the drop is small, it is round, spherical. But the bigger it gets, I have a little water mixed up with that, unfortunately. But you notice that the bigger the droplet gets, the flatter it gets. But the point I wish to make here is as follows. Supposing I bring two droplets of mercury close upon each other. I mixed this with a little water, which spoiled the effect somewhat. But supposing I bring them close upon each other. Watch them. Oh, look at that. Look at that. Well, as a matter of fact, the fact that I got the mercury a little wet with water has changed the surface tension properties, and it is not doing what I want it to do. Indeed, it is doing just what I don't want it to do, which raises some very exciting questions. But the point I wish to make is that when the drops coalesce, they go together with enormous forces and speed, and this is due to the electrical properties which the liquid possesses. So there we have surface tension, the shape of drops, and the shape and form of bubbles. And while I'm on this, I would suggest to you that there is a paperback book entitled Soap Bubbles and the Forces Which Form Them, written by an English physicist whose name was C.V. Boys, B-O-I-S, like boys and girls. And I would urge you to read it because there are hundreds of experiments there you can do with soap solutions, soap bubbles. Now more on the same. Here is a rectangular cubical frame of wire. I'm going to submerge it into the soap solution and withdraw it, and you notice the enchanting shape which we have here. Now, what must physicists say of these shapes? The shape which the soap has taken is a shape of least energy. And you will remember on an earlier program I remarked that the energy of a system tends toward less. So watch what happens when I puncture one frame. Watch. Oh, there it goes, and look at that beautiful shape. And now, there it goes. There it goes. Oh, there's another one. Always tending toward a surface of less energy. Now, why are raindrops round? The reason they are round is that they have the largest volume with the least surface. That's the property of a sphere, and hence their energy in this shape is the least. To show you that a circular or spherical form is always that toward which a system goes, I'm going to dip this ring in some soap, and here is a flexible loop of thread. Now watch what happens. I draw it out, and I have, it's not what I want. I draw it out. Oh, it's not what I want. Oh, well, I'll show it to you. Do you see that the curvature of this thread is circular? Let me try it with another one. I thought I had, oh yes, here's another one. Let me try it because there are some problems in doing, yeah, this is all right. Now, I'm going to puncture one film and watch the action, the motion of the string. Oh, there it is, into the arc of a circle. So the film above tends by contraction to a least energy. Further proof of this. Here is another ring, and here is a closed loop in here, a closed loop. I'm going to dip this into soap solution, withdraw it very carefully, and you see the loop inside is quite closed because of the tenacious holding of the soap film. Now I'm going to puncture the soap film in that little ring, in that little loop, and you will see it all go into a circular arc. Watch it, watch it. There it is. Now let me do break the film elsewhere in the larger part. Watch it, watch it. There it is, tending toward least energy. I'll do that once more because it's quite enchanting. Watch it. Oh, look at, oh, did you see how tenacious that soap film is? Now watch it. There it is. It goes into the arc of a circle. Here are two loops, side by side, and some interesting things can be done with them. Oh, I'm having a little trouble, and I may abandon it. Yes, let me suggest what you would witness. Let me suggest, because it's very important. Supposing you took a funnel and another funnel, and you dipped their front edges into soap and brought their faces together close and then separated them. What would you have? Well, the film would have that curvature, and that has a very special kind of geometry. That is called a catenary, C-A-T-E-N-A-R-Y, and that's the Latin word for chain. And indeed, if I took a chain here and held one end so and one end so, the curvature of that chain would be a catenary. And it is interesting to discover that in this shape, that film surface has the least energy, which is a fundamental principle of nature, that the energy of a system goes downhill. Now, since I am interested in blowing soap bubbles, I have here something I'm sure many are familiar with, a little pie plate with some soap solution and a ring, and there I make some bubbles. And I call to your attention their beautiful property. They are spherical. Oh, I thought I could catch that. Watch it now. Oh, I may be a little too impulsive. There it is, there it is. Watch it, watch it, watch it. Oh, I caught it, and it went through the other one, which suggests the tenacity of this business. Look at that. Now, what has this to do with other important matters in nature? I already said that raindrops are spherical, very important. And indeed, may I suggest, if you have a clothesline that hangs from here to here, the next time it rains, I urge you to look carefully at the raindrops that are hanging, the water drops that are hanging. They hang very, very sharply formed and all spherical. And now what do you see happen? These which are in a higher potential level slide downhill. This one hits that one, they coalesce and get bigger, and now the surface tension force is not adequate to hold up this greater weight, and it drops down. So here is a beautiful thing to witness. One last thing. Here is a wedge-shaped vessel, one of which, now held in my right hand, has water in it that is colored with food coloring, and the other has mercury in it. And I hope you see a very distinguishing feature. Let me show you quickly what that feature is. If I have a narrow tube immersed in water, the surface in the water would be so, and the upper surface in the tube would be so. In the mercury, the surface would be so. And this is very important for the affairs of nature, and I thank you for your attention.